Stochastics Statistics Seminar. It's a pleasure to introduce Arnaud Doucet, who is well known for his work on Bayesian methods, specifically on efficient computational methods for inference and learning in complex stochastic systems, on computational statistics and Monte Carlo approaches. He has been with the Department of Statistics at Oxford since 2011. And since 2019, he's also been a senior research scientist at Google DeepMind. He was an IMS medallion lecturer in 2016 and elected as an IMS fellow in 2017. And he's also been awarded in 2017 to 2020 the Guy Silver Medal of the Royal Statistical Society for his work on statistics. So it's a great pleasure to have him speak here on Ensemble projection sampling. Please take it away.
Thank you for the invitation. So I'm going to present a joint work with George Doligianidis, who is a colleague of mine in Oxford, on Sylvain Rubenthaler, who is a professor in the university in Nice, Sophia Antipolis, the south of France. And basically, I'll be talking today about yet another Monte Carlo method, which is basically which we'll be able to use so as to do perfect simulation for a class of statistical model of interest. Okay, so I'm just going to first start to kind of introduce a notation, and essentially here I'm going to be make it easy. So I'm going to consider that I'm interested in a distribution pi that admits a density pi, also denoted pi, okay, on RD. On it admits a density with respect to Lebesgue measure. On this density, what do I know about it? Well, it's of the form gamma x over z, where gamma x is essentially a normalized version of a density that I can compute exactly pointwise, but the normalizing constant basically is intractable. Okay, so for example, when you're doing Bayesian statistics, pi of x typically corresponds to the posterior distribution, to a given posterior distribution. And typically for all but simple Bayesian model, you have access to a normalized version of the posterior, but the normalizing constant, which is the evidence or the marginal likelihood, is intractable. Okay. Really, what I've been interested in most of my career is essentially how do you approximate such distributions. So when your D is in fairly large, so you have this complex high-dimensional distribution, well, there are two tools which have been primarily developed in computational statistics to obtain such approximation. So the first thing is basically to use MCMC. So what you do is you run a Markov chain, an ergodic Markov chain of invariant distribution pi, such as Metropolis, hybrid Monte Carlo, and I've done recently a lot of work myself on the non-reversible algorithm based on piecewise deterministic Markov chain Monte Carlo methods. Or there's an alternative class of techniques which are known as sequential Monte Carlo methods, which are essentially a combination of important sampling and resampling mechanism. Okay. So what is important is those techniques are actually powerful. They are very well established, but there's a lot of actually still interesting ongoing work. But essentially, what they do provide they provide you some kind of approximation of pi. So essentially, if you run your MCMC algorithm for a finite number of iterations, you get basically samples which are only approximately distributed according to pi. Similarly, if you run your sequential Monte Carlo method with a finite number of particles, well, it's going to return you an approximation at samples which are only approximately distributed according to pi. Okay. So today I'm not going to talk about that. I'm going to talk about something which is actually more exotic somehow, it's essentially self-contained piece of work, and which is going to be about essentially perfect simulation. So what I will present here, I want essentially to come up with a Monte Carlo method, which for a class of distribution I will specify later, return to me exact sample from pi. Okay, that's what I want to do in this talk today. Okay, so first, before basically moving to essentially the kind of description of my techniques, where I will perform a little, give a brief overview of the current literature on the perfect simulation. Okay, so it's very incomplete. Okay, so please bear with me. So the most famous technique so as to perform perfect simulation is rejection sampling. Okay, so it dates back to Buffon on it was popularized by Fermi and von Neumann, and it's an easy to understand techniques so as to do a perfect simulation, but typically it doesn't scale well in high dimension. Okay, so following that, there was a kind of very important paper published in 1996 by Prop and Wilson, which allow you to do perfect simulation for a much more complicated target distribution. And essentially what it's based on, it relies on, you have an MCMC kernel which has the invariant distribution pi, and you try to couple basically MCMC chains that would have started from any possible starting point in the sample space. Problematic if you have basically, if you work on RD, typically to be able to implement this algorithm, you need to have some kind of condition of identifying a partial order on the space, a monotonicity condition. So essentially, this technique is very elegant, but it's not broadly applicable to the class of model I'm going to describe today. Okay, and then following that, there were a few kind of variation of coupling from the past. There's one which was quite famous that appeared in the late 90s by Jim Field. That is some kind of mixture of essentially the mechanism that is behind CFTP coupling from the past on rejection sampling. And then we're still basically in the 2000s, there was a paper by Huber that said, okay, let's forget about all these kind of MCMC type ideas on, so as to do rejection sampling. Let's try to do some kind of new version of rejection sampling that is able to leverage the structure of, say, an high-dimensional target so as to use some kind of recycling mechanism so as to achieve perfect simulation. So I'm not going to go through detail. And it's nice when applicable, but it's typically applicable to distribution on discrete space. For combinatorial structure is not going to be applicable to the model I'm interested in. Okay. And then I would say there hasn't been that much basically in the field of perfect simulation for a long time. Okay, so you can see it's not really a hot topic for the time being. I've just mentioned papers still that basically are at least 20 years old. But there was a rebirth actually somehow of perfect simulation in the field of theoretical computer science. And in particular, there's been an interesting, very important, actually interesting, really, and I think important paper by Go, Mark Jerome, and Liu, which is they've developed this kind of a partial rejection sampling, which is also an idea where essentially you do rejection sampling, but you're able to do it essentially iteratively, so as to sample from complex combinatorial objects. Okay, so that's essentially, I would say, a brief overview of what is currently available in the literature. But all these techniques are not applicable to the class of model I'm interested in here. Okay, so what are we going to talk today? Well, we're going to talk about yet another rejection sampling algorithm, so as to sample from a specific class of distribution, which I call Feynman-Kac model. Okay, so I borrowed the terminology from Delmoral, my colleague Delmoral. And so some people I know don't like this terminology. They think it's actually not quite appropriate. So please bear with me. I just basically borrowed the terminology of my colleague here. So I'm just going to introduce this class of model, and then I will explain you how I'm going to basically try to do simulation from this class of model. Okay. So what is Feynman-Kac model? Okay. So there's a good review in the book of Pierre Delmoral that appeared in a Springer series in probability a few years ago. Okay, and it's very simple, essentially. So I'm going to deal only here with discrete time models. And essentially, it's going to be defined by a combination of two things. So first, you consider a non-homogeneous Markov chain. Okay, so such that the initial distribution of this Markov chain is new, and that follows potentially a non-homogeneous Markov kernel empty at time t. Okay, so you have this non-homogeneous Markov chain. That's one element of the construction. And the second thing you need to introduce to define your Feynman-Kac model is a sequence of essentially non-negative potential function. Okay, so that goes from the state space. Okay, so essentially xt will take value in say Rd, and basically it returns a non-negative value. Okay, and essentially what based on those two ingredients, what you call that the resulting so-called Feynman-Kac distribution is defined as follows. So assuming that essentially the product of the potential from time 1 to time big T is integrable with respect to the law of the non-homogeneous Markov chain, you can define this probability distribution. Okay, so this is essentially, you have here the distribution of the non-homogeneous Markov chain, and here this is basically the product of your potential. Okay, and you renormalize and have assumed it's integrable, so that defines you a distribution. Okay, so basically what I'm going to consider here in this talk is techniques so as to sample exactly from this such distribution, a subset of such distribution. These models are actually quite general, and they appear, as I'll show, in some rare event simulation problem, and also in particular in filtering problem, that is basically when you're trying to do a state estimation for a nonlinear, non-Gaussian dynamic system. Okay, and there are also applications in statistical physics.
Arnaud, I have a question. Those GTs, those potentials, they're given to you?
Yeah, they are given to you.
And you can do whatever you want with them? Like you can evaluate, take gradients?
You can evaluate them point-wise. That's all I will need later. And actually, I need more assumption. I will need them to be bounded. But for the time being, basically, I don't make any assumption for the time being, but obviously I will need to make a few later on.
Okay, thanks.
But the point is that what I will do will not rely on, say, pi being log concave or anything. Pi can be multimodal and so on. I will not use any property such as, say, log concavity. Okay.
But you will not have strong.
They don't need to be differentiable as well. So I won't need any of those things. Okay. Okay. So I give you a first example. So this is the setup of condition random walk. Okay. So assume you have a physical particle that evolves according to some kind of random walk dynamics. So, M here could correspond to some kind of basically discretization of Brownian or Ornstein-Uhlenbeck. Okay. And essentially it diffuses in the space, and whenever it gets out of some set S, basically it's absorbed and it's killed. Okay, so you could have basically it's like a particle diffusing in an absorbing medium, essentially. Okay, and essentially what you like to say, assume I give you such a model, and you might be interested in essentially at time capital T, you like to sample from the distribution of the particle path conditioned upon this particle having survived till time capital T. Or you might be also interested in computing essentially the probability that the absorbing time is superior to capital T. Okay? So these are two questions that are of interest, in particular to physicists. And there are actually quite a few papers in the physics literature about this problem. So, I mean, it fits completely in this class of Feynman-Kac model. So here in this case, we're going to take a potential, which is homogeneous. Okay, so Gt equals G, and it's just the indicator function of the set S. Okay, so it's easy. You can easily convince yourself that in this case, the Feynman-Kac distribution I had written, which we'll remember is essentially proportional to the kind of product of the distribution of your Markov chain time the product of potential. Well, in this case, pi construction, pi will be the distribution of the path condition upon staying in S until time t. Okay. And the normalizing constant of this distribution is the probability that the absorbing time is superior to t. Okay. So, as I said, there are actually quite a few papers in physics that are trying to sample from essentially such distribution. Particularly, there's a recent paper that appeared in Journal of Statistical Physics. So they are able to do that exactly, but under very, very restrictive assumption. on essentially the geometry, the characteristic of the set S, and also the dynamic, essentially, of the diffusive particle. Okay, so I'll show that we can do that. The kind of techniques I'm going to propose is much more generally applicable, actually. Okay. Another thing we can explain, so I'm going to skip this example, is just to show that something that is quite commonly used in statistical physics, known as the Jarzynski-Crookes identity, is also a Feynman-Kac model, but basically we don't have time for that, so I'm going to skip it. Okay, I'm going to focus on basically the following example, specific case of Feynman-Kac model, which is the class of essentially continuous state space model, also known as basically the Markov model. And the reason why I will focus on that is I think that basically it's much easier to understand the method I'm going to present in this framework. But keep in mind that my method is applicable to a much more general class of essentially Feynman-Kac model, including this problem of rare event simulation that I've just described. Okay, so what is essentially a state space model? You can think of it as a kind of a discrete time bivariate process with two components, xt and yt. Xt is a latent process, okay? So it's going to have, say, initial density, mu, and transition density that I keep homogeneous here, f, okay? So you don't have access to this process, it's unobserved, but you have access to a realization of the yt, and you assume that conditional upon x, the observation y are conditionally independent and follow some distribution g, okay? So basically, this is a very, very standard class of time series models, okay? So if here, essentially, you could have a linear, for example, Gaussian state space model, and here some kind of basically also linear equation, in which case you have like this, you have all this kind of linear Gaussian state space model machinery. X could be discrete value, okay? So in this case, you will have the standard finite state space HMM, okay? But basically, I will be dealing in my talk with essentially models where F can be non-linear, actually, and G also could be very complicated, actually. It doesn't have to be linear in X, could be non-linear, and could be general, okay? So now, how is this related to Feynman-Kac model? Okay, well, assume you have access to, so a realization of the process Y. So you have access to noise, to the observation Y1, Y2, YT. So I use a MATLAB notation. Then essentially you want to do inference about the latent process X1, X2, XT, where you can use Bayes' rule so as to basically characterize it. So the posterior distribution of the latent variable given Y, what it is, well, is proportional to the prior, which is given by this term here, which corresponds essentially to the prior density of the first T state of my latent process, time essentially the conditional likelihood. Okay, that's it. So that's basically the distribution on Z. In this case, Z, sorry, the normalizing constant is nothing but the marginal likelihood of my observation. Okay. So assume basically, so you have such a model, you'd like to be able to sample exactly from this posterior distribution. It's typically not possible. Whenever you have element of non-linearity or non-Gaussianity in your model, you forget about it. You cannot sample exactly from this high-dimensional posterior distribution. And I will present later on an example where T is of order 1000. Okay. But basically, there are one exception. There are actually two exceptions where it is feasible. Okay, this is the case where X lives in a finite state space, in which case it's possible to do that using kind of a modification of the so-called forward-backward method that has been developed a very long time ago by Baum-Welch in the 60s. And it's also feasible, it's also applicable to linear Gaussian state space model, in which case this distribution is simply in a very high dimensional normal distribution, and you can sample efficiently from it using some kind of Kalman techniques. Okay. So I will review basically the way you would sample from such a distribution if X was, say, taking value in a finite space, because this will prove actually useful for the rest of this talk lecture. Okay. So assume for the timing, forget about the like a continuous state space. Just think that xt takes value in a finite space. Or do you sample from this high dimensional distribution? So this is a discrete distribution in this case. Well, you use this following decomposition of the posterior distribution. So essentially, you rewrite it as basically the posterior distribution of the final state x capital T given the observation you've collected at time t. And then you basically consider this kind of backward decomposition. So you have a product of the conditional distribution of xt given the previous state, the next state xt plus 1 on the observation until time t. Okay. So what this expression tells you is that it tells you that once you have basically, once you're given t observation, y1, yt, your latent Markov chain is also a Markov chain. The condition Markov chain is the condition Markov chain, is the Markov chain of initial distribution pxt yt, which runs backward according to this transition basically kernel. Okay, so that's very simple. On this transition kernel here, they can be re-expressed basically in terms of the so-called filtering distribution, that is the posterior distribution of xt given the observation till time t, the transition probability of your system, and basically divided by the normalizing constant, which is the predictive distribution. Okay, so how do you leverage this decomposition of the joint posterior distribution so as to sample from basically the joint? Well, it's simple. You run this kind of forward recursion, think of it as Baum-Welch HMM recursion, to compute the filtering distribution on the predictive distribution. So do you run that in a forward stage? Okay. And once you've reached essentially time capital T, you sample from the final filtering distribution, and then you recurse backward by basically sampling according to this transition kernel. Okay, so that's a kind of forward filtering, backward sampling. Just think of it as nothing but some kind of sampling version of the famous Baum-Welch algorithm. Okay, so that's nice. It's elegant, and it only works for finite state space algorithm on linear Gaussian state space model, because otherwise you have no clue how to compute in closed form those expressions. Okay, but we will forget about that for the timing. We will see how to get around this problem further in the talk. Okay, so this is the class of Feynman-Kac model. And what I'm telling you is essentially the way I'm going to basically sample from such high dimensional distribution is going to be using rejection sampling. Okay. So first, we're just going to get back to kind of general framework where basically I'm interested, forget about Feynman-Kac model for the timing, just let's get back to the problem of sampling a generic target distribution pi, which you only have access to an unnormalized version of its density gamma. Okay, so if I'm just here recalling the standard rejection sampling algorithm. Okay, so this is simulation 101. It's just to introduce notation. So and then we will elaborate on this methodology progressively so as to be able to obtain a version that is applicable to Feynman-Kac model. So rejection sampling, the way it works, you basically need to introduce a proposal Q, okay, such that essentially gamma over Q is bounded by basically is upper bounded by a constant that I call W bar. So think of it that Wx is some kind of unnormalized importance weight, and W bar is essentially an upper bound on this weight, okay? And when you're basically in this scenario, you can basically apply directly rejection sampling. So how does rejection sampling works? Simple. You sample a candidate from Q with probability, basically Wx over W bar, you output X. Otherwise, you return to step one. Okay? That's it. It's well known. I'm not gonna basically, you all know that rejection sampling returns an exact sample from pi. The average acceptance probability is given by essentially Z over W bar, and the expected number of iterations until acceptance is the inverse of this essentially average acceptance probability. So it's all standard. Okay. So that's going to be the basic tool I'm going to use. So the first thing I'm going to say is, well, I'm not happy with rejection sampling. There's no way, obviously, it's going to scale in the scenario I'm interested in, because I'm interested in scenario where I'm going to have at least, you know, T variable x1, x2, xt for Feynman-Kac model. And I know that essentially the average acceptance probability of rejection sampling typically degrade exponentially fast with T. So that's not, I need to improve over importance sampling if I basically want to develop a practical method. Okay. So the first thing I'm doing is I'm going to basically ask myself the question, without making any additional assumption, that is, I only have access to a distribution Q, and I know that gamma over Q is bounded by W bar. Can I come up with basically a new proposal distribution that admits a higher average acceptance probability than standard rejection sampling? So that's the first question I'm asking. Okay. So I'm telling you, it is feasible. It's going to work as follows. So what I'm proposing to do is the following thing. Okay, so the only thing I can do is sample from Q, because the only thing I've been given, I don't want to make any assumption. So I sample and IID sample from Q, okay? And I build an importance sampling approximation of pi, okay? So basically, I'm gonna essentially use normalized importance sampling. So here, basically, I have weights which are basically normalized so that they sum to 1. I base a normalized importance sampling approximation of my target distribution, okay? And what I do, once I basically computed this importance sampling approximation of the target, I sample from it, okay? So that's not a new idea. And this is, for example, known as sampling importance resampling, and I was introduced, I think, by Robin first in an old JASA paper in 1987, okay? And he was saying that's one way to obtain approximate sample from pi. And it seems like a sensible idea indeed, but me, I don't want to do that. I don't want to get approximate sample from pi. I want exact sample from pi. So I'm not happy with just this mechanism, okay? So I'm just basically going to use this mechanism to build a proposal distribution for rejection sampling. But you see, I'm not happy with it for the time being, because clearly the distribution of such a sample is not equal to pi. There's going to be some bias, actually. Okay. Okay. So essentially what I want to do is I want to put this kind of sensible proposal mechanism into a rejection mechanism, into a rejection basically sampling type algorithm to obtain exact sample from pi. But I cannot do that directly. And the reason why I cannot do that is because the distribution of the sample I obtain by using this kind of sampling algorithm, building an importance sampling approximation of the target and resampling from it, well, it gives you a distribution which is not tractable, because this is essentially, think of it as the expectation of this weighted empirical measure with respect to the distribution of x1, x2, xn, okay? So, I mean, you basically, this is the marginal distribution of x, okay? But you don't know this distribution. It's basically, it involves some kind of intractable expression. So how are you going to be able to essentially exploit that into some kind of rejection sampling mechanism? Well, we know that it should be possible to do something like that because this kind of basically proposal mechanism has been already previously used so as to essentially build independent metropolis hasting algorithm which target pi. So in particular, we have such a construction appear in an early paper by Christophe Andrieux and myself. Okay, and this also been rediscovered recently in machine learning, where they use the same construction to do essentially variational inference. However, we'll see that the construction that is used in those papers is actually not good enough essentially for what I want to achieve. But essentially, what those papers, earlier paper, my previous experience told me that it's possible to basically essentially use such essentially sophisticated proposal distribution. And the way we do it, well, is by using some kind of auxiliary variable construction. Okay. So before explaining this construction, I'm going to present you the algorithm. What's the algorithm? How it is working. Okay. So this algorithm is going to be ensemble rejection sampling. So instead of sampling, one proposal from Q as in standard rejection sampling, I sample N, IID sample from Q. I build my basically weighted empirical measure approximation of pi. This is just important sampling. And I also compute essentially the unbiased estimate of the normalizing constant, which is just basically an average of the importance weight. Okay. Okay. So now I obviously need to introduce some kind of thinning mechanism so as to essentially reject my proposal. Okay, so what do? I do the following thing. So I've got Z hat, which is this unbiased estimate of my normalizing constant. And I'm going to basically come up with an upper bound on Z hat. And the upper bound on Z hat is obtained as follows. So basically, I remove 1/n times the importance weight of the particle I've selected. Okay, this is X here is my sample from the weighted empirical measure. And I replace that by the upper bound basically on the importance weight. Okay, so this thing by construction is an upper bound. Z bar is definitely by construction an upper bound on Z hat. Okay, and then I accept with probability Z hat of a Z bar X. Otherwise, I return to step one. Okay, so that's my algorithm. It doesn't require knowing more than basically what is used in standard rejection sampling. It's applicable whenever standard rejection sampling is applicable. Okay, so what can we say about this algorithm? So my claim is that this algorithm returns an exact sample from pi. Okay, so when it output X, this X is distributed according to pi. And the average acceptance probability of a proposal satisfies this expression. Okay, and in particular, is superior to, so here, remember that this is the average acceptance probability of the standard rejection sampling. So here I've got a lower bound on this, on the average acceptance probability of this ensemble rejection scheme. And in particular, you see something quite nice is that as n increase, okay, this lower bound converges to 1. Okay, so it's good. So I've come up with a way to essentially debias, if you want, this kind of important sampling approximation of pi. Okay, so how do you prove that? So this is going to be essentially the only technical slide in my talk. Okay, because everything I do in a more complicated case is just variation over the same idea. So how do you prove that? So with sloppy notation, I apologize, I didn't put the basically measure theoretic notation to simplify. So what I say is essentially I rewrite everything on an extended space. So what I say, okay, I couldn't compute the marginal distribution of X under my proposal mechanism because it's involved intractable integral. So what I do is I basically rewrite essentially explicitly all the random variable I use so as to sample X. Okay. So what do you do basically? so as to sample X, well, remember my algorithm, well, you sample N proposal from Q, then you build basically an important sampling approximation of pi on you sample from it, but this is equivalent to essentially selecting particle K among the N particle according to probability, which is equal to this quantity, on setting X equal to XK. That's all it does. So this is just rewriting my proposal mechanism in a kind of extended way, if you want. Okay. Now, the second thing we do is, remember, I got sample from this essentially high-dimensional proposal distribution, and I accept those sample with probability Z hat of Z bar. Okay, and Z hat of Z bar is always below 1 by construction. So so there's no probability, it's indeed a probability. And if by construction, my accepted sample, well, they have to be proportional to Q times Z hat of Z bar. This is if you pick basically some proposal distribution Q and you accept with probability alpha, basically the resulting sample have the density proportional to Q alpha. So that has to be of this form. Okay. So now if I want to prove that my algorithm is correct, the only thing I need to check is that the marginal distribution of X under this distribution pi bar is indeed pi of X. Okay. So the way you do it, so you do a bit of an algebraic manipulation. So we know from, so actually I'm just going to skip a thing, but essentially you can show indeed, and this is really algebraic manipulation, that essentially pi bar of this funny distribution and sampling from using this ensemble rejection sampling algorithm is a distribution which accepts by construction a marginal which is pi. Okay, so X under pi bar is distributed according to pi. Okay, so that's the simple construction. So how did I come up with this construction? I came up with this construction because basically we had done previously a construction on extended space which corresponded to essentially an alternative extended target distribution and so on and so forth. Anyway, so it's irrelevant for this talk, but basically this is the way I got the idea. Okay, so that's nice. You can easily get in free line basically also I obtain my lower bound on the average acceptance probability. It's just a simple change of measure followed by Jensen inequality. So it's literally elementary mathematics. Everything here in this talk is about this construction, this kind of strange construction. And indeed, it's perhaps a bit strange when you first look at it. Okay, so this is this ensemble rejection sampling. Is it interesting? Is it an interesting algorithm? Okay. Well, what's the expected number of proposals from Q you need to obtain a sample from pi? Well, I know that for standard rejection sampling is the inverse of the average acceptance probability. Okay. And for ensemble rejection sampling is the inverse of its average acceptance probability times n. And why times n? Because each iteration of ensemble rejection sampling involves n proposal, not one. Okay. So I only have an upper bound on this guy, but you see, okay, this upper bound might be loose, but at least it's tight for n equal 1. But we see that, well, that's not good. That's not good because actually, when you factor in the fact that essentially each essentially application of this ensemble rejection sampling require n proposal, it seems that it's actually quite useless. Okay, so really, it's not that great. So could we do something a bit, at least? Is there something that you can basically get out of this algorithm? For the timing, it seems completely actually inefficient compared to standard rejection sampling. Well, you could claim that it's actually quite interesting because once you accept essentially a candidate in this ensemble rejection sampling algorithm, well, I've written previously as just accepting the proposal X, but actually if you rewrite everything as accepting a sample from this kind of auxiliary distribution pi bar, well, you can reuse everything to obtain essentially some kind of lower variance estimate of expectation with respect to pi. But to make a long story short, it's not interesting algorithm. So why the hell did I spend my time explaining you that? Because it seems that actually this algorithm is of limited interest for the timing, okay? Well, I will show that although this algorithm, the kind of first version of the algorithm, which is ensemble rejection sampling version 1.0 as indicated in my slide, is actually useless, I will see I can extend this algorithm so as to sample Feynman-Kac models, and in this case, it's going to become interesting. So, but the important thing was for the timing, it was to understand that you can basically, there's a modification of rejection sampling that you can use that increase essentially the average acceptance probability of a proposal. Okay. Okay. So now that we've got basically, we've understood this kind of ensemble rejection sampling, I want to basically modify the algorithm so as to sample from basically a Feynman-Kac distribution, okay? And I will present everything here as basically in the context where I deal with state space model, but you can replace here the small g by a capital GT. You can replace F by MT, and everything goes basically as described in the rest of the talk. Okay, so I want to sample from that. I'm going to use the same idea. Okay, so I'm going to say, look, okay, sampling from this high-dimensional complicated distribution, this is very complicated. So what I'm going to do is I'm going to build first an important sampling approximation of this target distribution, as in ensemble rejection sampling. I'm going to sample from the important sampling approximation of this target, okay? And I will correct for the bias using basically an accept reject mechanism. So that's what I want to do. Okay. So the way we're going to do it is a bit funny. So at each time, so now I've got basically to a distribution on the product space x1, x2, xt. Okay, so basically what I'm going to do is I'm going to sample n particle at time 1, x11, x1n, all IID according to distribution q1. Then at time 2, I'm going to sample similarly x21, x2n, IID according to q2, and so on and so forth till time capital T. Okay, so what I do is basically, it's just I draw a random grid on my space. That's all I'm doing, actually. Okay. Now, from those samples, so I've got n sample at each time instance, okay? I can build n to the power t state sequence by combining them. So I can basically pick any particle at time 1, combine it with any particle at time 2, and so on and so forth. If I look at all the possible paths I can build this way, I can build n to the power t of them, obviously. Okay? And marginally, they're all distributed according to this following product distribution. Okay? Because x1 follow from q1, x2 from q2, and so on and so forth. Okay? Okay? And now, once I've got those nt particles that are all identically distributed, I build my importance sampling approximation of my target distribution pi. Okay? So the way you do, you have is just naive importance sampling. So here, these are normalized importance weight, which are proportional, sorry, to this complicated expression. So this complicated expression is nothing but pi divided by the product of qt from t equal 1 to capital T. So this thing is nothing but essentially an importance weight between my high-dimensional target, pi, and my high-dimensional proposal, which is given by this product of qt. That's it. Okay. So now I've got this really high-dimensional, I have this important sampling approximation of my target distribution, and I sample from it. Okay, so that's going to be my proposal mechanism. So because I'm doing important sampling, I need to make assumption basically on my importance weight. So I need my importance weight to be bounded. There's no miracle, okay? So essentially, remember that the importance weight I'm going to have are basically the product of such terms from time t equal 1 to time t equal capital T. And I'm going to assume that each of these individual terms is bounded over the argument xt minus 1 xt. And this is the main restriction of my algorithm, because for this thing to be bounded, it does restrict the class of models you can basically apply my methodology. Okay, so that does limit the class of model to which ensemble rejection sampling is applicable. Okay, but as I'll show in my simulation, you can read the paper, there are practical important problems which do satisfy those assumptions. Okay, so now basically I have done these crazy things. I've done this random grid discretization of the space. Okay, I say from there I can build n to the power t capital paths, which are all marginally distributed according to the product of the qt t equal 1 to capital T. Okay, and then I do my important sampling approximation. I sample from it, and I obtain basically a proposal. And the distribution of the proposal is given by this expression. So this is once more intractable because it's the expectation of a weighted empirical measure with respect to a lot of particles. Okay, so we'll get around that using once more a Noxera variable trick. But first, there are two things we can ask ourselves. The first thing would be, what? You have a distribution which could be in thousands of dimensions you're trying to target. Okay, because pi, here I'm going to have example where t is of order 1,000. So you're doing so as to basically sample from it. You're using an important sampling approximation of it. And if you know Monte Carlo well, you tell me, well, that will never work because typically important sampling doesn't work. Degrades exponentially fast in high dimension. Okay, but don't forget here that basically, indeed, important sampling, basically performance typically degrade exponentially fast with dimension, but I use an exponentially large number of samples to approximate the target. So I fight that by using not a number of samples which is independent of the dimension of the target, but the number of samples I'm using is exponentially large in the dimension of the target. So that's why I do have hope still that this proposal distribution is doing a good job. Okay, so that sounds okay. That sounds a good idea, but it's good to use an exponentially large number of important samples so as to build your proposal distribution. But how the hell do you basically compute pi, actually? Are you going to basically do that? Well, because if you try to essentially construct pi hat, well, it's a sum of n to the power t term. So you're not going to be able to compute that. So how useful it is? Well, the point is that you don't need to basically compute pi hat explicitly. The only thing you need to do is sample from it. On sampling from it, what I'm going to show is that you can achieve that in computational complexity n squared t, okay, instead of n to the power t. So the way you do that, and it's a remark which is as follows, is that so as to sample from pi hat on n's from q bar, your proposal, on computing the normalizing constant, you can essentially sample its equivalent, entirely equivalent, to sampling from the posterior distribution on computing the likelihood of a finite state space hidden Markov model. Okay? It's a hidden Markov model, finite state space hidden Markov model, whose states have been defined by the random grid I've basically sampled at the beginning. Okay? So that's the key remark, actually. So essentially, you can reuse, in particular, this kind of forward filtering, backward sampling algorithm that applies to finite state space Markov model to this embedded, basically, finite state space HMM, so as to do those calculations. Okay, so that's the kind of nice thing about it. And the point is that the combinatorial cost of doing that is n squared over t. So essentially, you leverage some kind of dynamic programming recursion so as to achieve that. Okay, so that's nice. And similarly, remember that in my basic ensemble rejection sampling, you needed to compute an upper bound basically on Z hat. Well, here similarly, you can compute an upper bound Z bar on Z hat using some kind of modified hidden Markov model recursion. Okay, so essentially, it's cost you again order n squared t. Okay, so if you're interested, we don't have time, but so I should mention that this idea first, before moving on, I should mention that this idea is inspired by the so-called embedded HMM method of Radford-Neal, actually. So he came up with an idea. So he doesn't do exact simulation. He doesn't use important sampling, but he used some kind of this kind of embedded HMM mechanism in some kind of GIP sampling algorithm, so as to sample the posterior distribution of the latent state in a state space model. Okay, this is where I got the inspiration from. Okay, so the way it looks. So I'm not basically essentially go in detail for it, but essentially, once you sample your random grid, okay, then you run first this forward recursion here, which is the forward HMM recursion, okay. So you compute the kind of filter and predictor from the embedded HMM, and then you have you sample backward. And this is, you have a backward sampling phase, which is given by this expression. Okay. And you have once more a kind of modified algorithm to compute your upper bound on the normalizing constant. Okay, but it's irrelevant. Just keep in mind, it's just essentially Baum-Welch applied to this kind of HMM defined by this random grid. Okay. So the algorithm proceeds as follows. So to recap, you draw your random grid, you sample from this really high dimensional important sampling approximation of the target, and you compute the corresponding estimate of the normalizing constant using this kind of HMM recursion. You use another HMM recursion so as to basically obtain an upper bound on Z hat. You accept with probability Z hat of Z bar. The claim, using arguments which are very similar to what I've described before, this procedure returns an exact sample from pi, and the average acceptance probability of the proposal goes to 1 as n goes to infinity. Okay, so that's nice, but it doesn't tell you that this algorithm is more efficient than a brute force in rejection sampling. I told you in the case where you would have t equal 1, it's not interesting. Actually, we've seen that in the case where t equal 1, this ensemble rejection sampling algorithm is not better than standard rejection sampling. Okay? So what about, let's try to understand what happens basically to this kind of ensemble rejection sampling applied to sequence. So I'm just consider the case where you have basically a product target on a product proposal. Okay, and my algorithm doesn't know about that. Okay, so what I know is that in scenario, the rejection sampling has an acceptance probability that degrades exponentially fast with t. If you redo the calculation for this algorithm I've just proposed, then you know that essentially the average acceptance probability of this algorithm is essentially lower bounded by a quantity of this form. And in particular, if n increases linearly with t, this basically upper bound is basically its control. Okay, so you have this thing that it doesn't vanish as t goes to infinity. Okay, so essentially you just need to have n over the t. So that's for a very simple model. Now apply it to Feynman-Kac. Okay, so more realistic assumption where the target doesn't factorize. So under basically condition of the incremental importance weight, which are very similar to what is found in the basically particle filter literature. You obtain a lower bound on the acceptance average probability that doesn't vanish as soon as basically n increase proportionally to t. Okay, and because basically the computational complexity of my whole procedure is of order n squared t, it tells you that essentially to obtain a sample from pi, the expected computational cost is essentially of order t cube. Okay, so you went down from exponentially bad. So the standard method is exponentially it's exponential in t, and we are back to cubic in t. Okay, so it's finishing. So I have some application where for this kind of basically simulation of particle in an absorbing medium, we sample distribution basically in dimension up to 1000. And you see that basically if I use, for example, in this scenario, 5,000 particle, basically the acceptance probability in 1000 dimension is 17%. Okay. So I've got example for state space model which are found in the econometrics literature. So we managed to sample actually here. It's not so efficient actually, but we can still sample a distribution which is 200 dimension. Okay, with 5,000 particle acceptance probabilities about 8%. And here, this is a toy example which is found everywhere in the particle filtering literature because it corresponds to a very highly multimodal target distribution, posterior distribution, so that standard MCMC would never work on that, actually. And we can apply again the algorithm, and we could sample from this really high dimension, like this 500 dimensional multimodal target distribution. We had an acceptance of average acceptance probability of 5% when we use n equal 1000 particle. Okay, so essentially, we have this kind of algorithm that allows you to sample perfectly from a class of Feynman-Kac model. It can be extended to also kind of directed continuous value this graphical model because there's an equivalent of the forward filtering backward sampling. So this is directly applicable. Okay. So the expected computational cost is essentially under regularity, is essentially in t cube, but it's important to understand in term of is still scaled exponentially badly in the dimension of single state xt. Okay, that we haven't done anything about that. As I said, unfortunately, this construction is very fragile. So you might be tempted to do like cleverer thing, like trying to have a random grid. You're trying to do some stratified sampling to build your random grid, or you're trying to use something like more clever to build your grid, such as a particle filter. None of this extension seems to work. I tried hard. I could never make it work for cleverer proposal. So it's all rely on this kind of fairly brute force on unintuitive discretization of the state space, which is not satisfactory. And finally, so we tried. So there's a way to get around that. Okay, so which is to use proposal, which instead of using this kind of rounded grid proposal, we use some kind of branching particle system on some kind of dominated coupling from the past. But it's nice. It's more generally applicable than what I've described, but it's also much harder to implement onto study. Okay, that's all. Thank you. And sorry to have gone over by 3 minutes.
All right, thank you very much, Arnaud. Given the time, maybe we can have one question from the audience. I don't see anything in the chat.
Okay.
Let me just start. Maybe does your method extend if you miss some of the observations? Why?
Yeah, you can. Yeah. So actually, there's a part in my paper where I explain that.
Okay.
Yeah, you can do that. Yeah.
Any other questions? All right, so let's thank virtually Arnaud, and maybe you can send questions directly to him by email. Thank you. Thanks very much. Bye.